All right, guys, welcome to the second part of Remote Day here. What we're going to talk today, or in this little video, is about net change, or how integrals can represent net change, or the change in a value. And it's actually, I think, a pretty simple concept to grasp. So let's just start off by maybe thinking about um, the fundamental theorem of calculus, and such that the integral from a to b of f of t was just equal to the antiderivative, right, of b minus the antiderivative of a. We've done that a million times now. You should be well versed in that, okay? That just the area under the curve, or the integral of f from a to b, however you want to think about it, is equal to the antiderivative of b, antiderivative of f at b minus the antiderivative of f at a, okay? So if we just do a little simple algebraic manipulation, if I add capital F of a to both sides, I could rewrite this expression as f of a plus integral from a to b of f of t dt. That will be equal to capital F of b. All I did again was take what was above and just add a f of a to both sides, capital F of a. So what's the implication here? Well, the implication here is that, let's write this out, that the value of f at a, so the value of capital F at a, okay, or the starting value, right? Well, maybe I'll say this. Starting value of f at a plus, right, the change in f is going to equal your ending value of f, okay, which is, right in this case, b. So all I had to do is reorganize this expression from above to basically say my starting value plus the area under the curve, which we all know to be change in, if you're thinking velocity, change in position, it's change in whatever units we're talking about, right? Your starting value plus your change in units is just going to equal your ending value, where you end up, okay? And if we can grasp that, it really allows us to kind of do a lot of different things. So really, just to drive this home before we kind of go into the meat of all this, let's just quickly run through a few things, and let's just talk about what it means. So let's start off with this. If h of t is the rate of change of the height of a conical pile of sand measured in feet per hour, what does the integral from 0 to 5 of h of t dt represent? Answer in the correct units. Well, we do know, again, that integral represents change, right? So this we would say is that it represents the change in sand. So if my function is rate of change of the sand, the area under the curve would be the change in sand, okay, in feet. And let's be very specific. It's not over the whole course, of the history of time. It's from time t equals 0 to t equals 5, okay? I would encourage you maybe to pause the video, try answering 2 and 3 just in English, and then follow up, hit play, and see if your answers match mine. Okay, hopefully you've done that. Okay, let's just do these quickly. If v of t is the velocity of a particle moving along the x-axis, measured in feet per second, what does the integral from 3 to 10 v of t dt represent? Answer in correct units. Okay, we've done integrals with velocity a lot, so hopefully this one was a little bit easier. Okay, it just represents the change in position of the particle, and we want to be very specific, of the particle in feet from time t equals, not 3, or not 0, sorry, 3 to t equals 10. Okay? And then if b of t is the rate of growth of the number of bacteria in a dish measured in number of bacteria per hour, so another rate, what does the integral from 2 to 6 of b of t represent? Again, answering in correct units. So I would just say that it represents the total change in bacteria from time t equals 2 to t equals 6, okay? So really what I'm trying to drive home here is we have to really intuitively understand what an integral of a function tells us. And again, the integral of a rate is going to give me the change in whatever that rate is measuring. So if you're measuring, again, rate of sand, then the integral would represent the change in sand. If you're measuring change in velocity or some type of motion, right, your area under the curve is going to represent your change in position. Okay, so that is really important. It's always the change in something, okay? So let's kind of put this all together. So if we go to the next page, it says, if v of t is the velocity of a particle moving along the x-axis at time t, and the position x of t is 5 at t equals 2, A, write an integral expression that represents the position of the particle at time t equals 10. We'll do B in a second. So again, if I want to know where it is at time t equals 10, I need to know where it starts, and then I need to know how much it changes. So really, all I need to do for A, for my expression, is to say where it starts at time t equals 2, which is at position 5, and where it's going to end up at time t equals 10 is going to be where it starts plus the change in its position from 2 to 10. Right? So that, I'll even say, equals x of 10. Right? So its starting value plus its change in position is going to tell me where it ends up at 10, right? And then write an integral expression that gives the total distance traveled by the particle from times t equal 2 to t equal 10. Well, total distance traveled means, again, I'm not looking for the displacement or change in position. Like if, for example, if I start at 0 and the particle goes 3 feet to the right and then 3 feet back to the left, its change in position is 0, but its total distance covered is 6, right? 3 to the right, 3 to the left. So only thing you have to do to change your integral to go from 2 to 10 is I don't necessarily want to know what the integral area under the curve is of v of t. I want to know is the absolute value of v of t. And really, if you think about what that's doing, is that it's going to just make sure any areas that fall underneath the curve that we would normally assign a negative value, it's going to make it positive, right? So any areas underneath the curve that are below the x-axis will become positive by adding that absolute value in. And that will just give you total distance covered, not necessarily net change, all right? So those absolute values are critical. I'll even write the note. Don't forget the absolute value. Okay, that's quite important. All right, again, this is kind of more or less it. Let's maybe skip ahead to number 6, and let's maybe try to do that one together, and then I'll let you start the homework for this section. All right, so it says, given dy over dx equals 3x squared plus 4x minus 5, with the initial condition that y of 2, so the antiderivative to dy dx is -1, find y of 3. So let's remember, if we want to find y of 3, we need to know where it starts at y of 2, which we'll fill in a second, plus the change from 2 to 3 of my function. That's going to tell me where I end up, right? So y of 2 we know to be -1, so I'm starting at -1. Let's integrate this guy. If we integrate him, we get x cubed plus 2x squared minus 5x, and we're evaluating that integral from 2 to 3. That's going to give me the change, okay, in y. Okay, that's going to equal my y of 3 value. So if we integrate this just to save us some time, the integral from from 2 to 3 of that function, or that integral, is just 23. So plus 23, and if you want to do it out to prove it, you can do it. Equals y of 3. Combine those two. That gives me 20. Oh, sorry, I take it back. It's not 23, it's 24. I'm looking at the wrong thing. Sorry, it's 24, which means y of 3 is just 23. Okay? So again, just to repeat this, again, this is what I mean by net change, right? I had a starting value. The integral area, the integral of the function will give me the change in that function, okay, and that's going to equal my new value, okay? All right, so your homework, some of these you need a calculator for, like number 7. We'll do some calc stuff in the next couple days, but for right now, you can skip. All I want us to do are problems number 8 and 9 for homework. Again, I think they're good problems to do. So take a look at those. There's really no math, actual integrating to do. You really just have to interpret the areas under the curve. So again, use my solutions to check your answers on those and come in with questions tomorrow.